Welcome back to Lecture 7. In the last part of Lecture 7, what we saw was a new form of Maxwell, integral Maxwell with respect to past strain rate. This form is written explicitly in terms of stress, which allows us to easily calculate what the state of stress now, at current time, is in a viscoelastic system as a function of its deformation history throughout past time. Remember those two time scales. Current time now is constant, and we write it as t. Past time is a continuum over which current time results, t dash. So past time goes from the dawn of time, t dash equals minus infinity, through to t dash equals t, current time. What we saw was that our integral Maxwell model predicts exactly the same results as our differential Maxwell model, which is good from a mathematical standpoint, because it means that we haven't made any errors. We haven't added any additional physics yet, so we don't expect the results to be different. The integral form that we derived, however, allows us in the future to add in more physics that we can use to try and remedy some of the shortcomings of the simple Maxwell model. What we're going to do in this part of Lecture 7 is do a quick worked example of how to work out stress through a more complex deformation history that could be, example, an approximation of something you might find in an extruder or other piece of processing equipment. So let's have a quick look at the deformation history we're going to be examining. So here on the blackboard we have strain rate gamma dot plotted as a function of past time t dashed, and the blue arrow on the far right hand side is where t dash equals t. That is current time. Ultimately, current time is where we want to calculate the state of stress for this material. We can see that our deformation history has in effect four regimes. We have a period of no deformation from t dash equals minus infinity through to t dash equals 0. Then we have a step change in our deformation rate between t dash equals 0 and t dash equals t1. Our deformation rate goes to gamma dot 1. Then we have another step change of deformation rate between t dash equals t1 to t dash equals t2, where gamma dot increases from gamma dot 1 to gamma dot 2. After t dash equals t2, we can see that once again our deformation rate is 0, and that it is in this period that current time exists. So let's divide up this deformation history as regime 1, regime 2 and regime 3. Now, a few notes. This deformation history could be, for example, an approximation of what you might find in an extrusion system. Before t dash equals 0, your polymer's at rest, maybe in a feed. In the period 1, you may find your polymers being conveyed by the screw in the extruder. Fairly low shear rate, but non-zero. In period 2, you may find your polymers being squeezed through an extrusion die, typically high shear rate, big pressure drop. Regime 3 might correspond to when you have your extrudate in open air, and there's no strain rate being applied to it any longer. Now, there's no reason why these strain rates have to be constant. I've put them constant here because it makes illustrating the point I want to get across a lot more easy, because you don't obscure it in a lot of mathematics. Be aware, however, that Tripos examiners love making these deformation rates non-constant, just to give you something extra to think about. So what we're going to do is to examine how we use integral Maxwell to get the state of stress at current time, t, and what we're going to do is we're going to apply that model to each of these three regimes. We're not going to bother with the regime prior to t dash equals 0 because our deformation rate, gamma dot, is 0 at that point in time. So let's examine regime 1. Now, when we look at a regime, what we do is we put current time somewhere in that regime. So I've now moved current time into regime 1. Let's work out integral Maxwell now exclusively for regime 1. So there is stress at current time, and it's equal to my deformation rate, gamma dot 1, multiplied by the integral that we saw last lecture. Now, if we look at the limits on this integral, it's going from 0 t dash equals 0, which is where my deformation regime starts, to t dash equals t now. And so this expression, very simply, gives us a state of stress within regime 1. We're going to do exactly the same for regime 2. Gamma dot has now changed from gamma dot 1 to gamma dot 2, and I have moved current time into regime 2, sometime after t dash equals t1, but before t dash equals t2. What I write here now is a sum of two integrals. The state of stress in regime 2 depends on the entire deformation history of my system, which includes regime 1. So the first term on the right hand side corresponds to regime 1, which is what we wrote last time. But note now that the upper time limit has moved from t to t1, so we capture the entire history due to regime 1. The second integral, note that the deformation rate has changed from gamma dot 1 to gamma dot 2, and the limits on the integral go from t1, which is when it starts, to t current time now. Okay, so that gives us the stress as a function of current time when current time happens to fall in region 2. Now, let's have a look in the final regime, regime 3, and let's write down the integral. And if you recall back to last lecture, the integral when you have a regime of 0 shear rate, well, you ignore that regime, you just have to pay attention to the integral limits on the previous regime. So at first sight, the integral I've written on the board is identical to regime 2, except for one very important thing which I've highlighted in red, which is the upper time limit on the second integral. Rather than it being current time, when I was in region 2, current time now falls in region 3, so the upper limit on that second integral is the end of region 2, t2. Okay, so let's recap. I have three equations. I have stress at current time when current time falls in regime 1. Likewise, I have stress at current time when current time falls in regime 2. And finally, I have stress at current time when current time falls in regime 3. Now, let's plot each of these equations out on the graph. So here is my deformation history. If I wanted to plot stress on this graph as well, I would use each of the three equations I've derived in the regime that it's applicable to. So I'd use the equation 1 for regime 1, and there's my stress growth. In regime 2, I would use the equation that corresponds to regime 2, and then there's a further stress growth. And then in regime 3, I would use the equation that corresponds to regime 3, which is my stress decay. If all I cared about was what's happening at t dash equals t when current time is in regime 3, I just have to use the equation for regime 3. But if I want to work out what the profile of stress is throughout the system, I have to use each of the stress equations that correspond to each of the regimes individually. So there you have it. There's a worked example. Now you could imagine, for example, that in each of these regimes, gamma dot is maybe directly proportional to past time or quadratic in past time, which just makes the maths a little bit more in-depth. But the concept, from what I've illustrated, does not change. So let's recap some key points. Hopefully you'll think it's now relatively straightforward to look at deformation histories. You just write integral Maxwell with respect to each of the regimes that you're looking at in terms of deformation. Each strain rate regime has its own result, and if you're interested in the stress within that particular regime, that's the result you apply to it. So don't apply equations from different regimes into other regimes, otherwise you'll get the wrong answer.